Welcome everybody for attending today's webinar, Stay on Target, Connected CAD and FEA of Composite Materials with 3DEXPERIENCE. To begin, I just want to do some quick housekeeping here. First of all, please use the chat to interact with myself and other moderators of the webinar in case you're having any problems. Also, in case there are any questions, please use the Q&A section of the Goldcast interface to submit questions. We'll be monitoring these questions throughout the course of the webinar. All right. So, agenda for today is we're going to start off with an introduction to myself and my co-presenter, and then we're going to get pretty deep into composites, really starting at a very ground level, and then we're going to build up the complexity as we go. We'll start off talking about CATIA Composites and how CATIA enables composite design. And then we'll shift gears a little bit from there and talk about how we can then take those CATIA composites into simulation using the 3DEXPERIENCE simulation rules. And then we'll talk about how this kind of coupling of technology works back and forth to make design changes and to do updates and those types of things. So that's our agenda for today. Again, if you have any questions, comments, concerns, please use the Q&A portion of the chat as we go through.
Hello, my name is Tim Ramos, and I am a Senior CATIA Specialist with GoEngineer. Prior to my current role, I worked as a body design engineer in the automotive industry, developing both sheet metal and plastic injection parts, utilizing both advanced surfacing and solid design techniques. In my off time, I enjoy DIY and restoration projects, as well as designing and 3D printing random accessories and widgets. I received my bachelor's degree in mechanical engineering from Rensselaer Polytechnic Institute in 2014. I am a certified CATIA expert through Dassault, but also have 10 plus years of CAD experience in various authoring softwares.
And my name is Matt Sherak. I am a Senior Simulation Product Specialist here at GoEngineer. I've been working in the simulation field and design field for a little over 8 years now after I got my Bachelor's of Mechanical Engineering from Metro State University of Denver. Most of my experience has been with SolidWorks finite element modeling and fluid dynamics, but recently I've been digging deeply into Abacus finite element modeling and the 3DEXPERIENCE tools and the integration between those two.
Composites 101. What is a composite? Essentially, a composite material comprises two distinct materials possessing specific properties. When these materials are combined, a new material with improved characteristics is produced. One material consists of fibers, called the reinforcement phase, while the other is a continuous substance known as the matrix phase. In composite materials, the matrix phase bears a load over a large area and transfers it to the reinforcement phase, which primarily shoulders the load, but only along the fiber direction. Thus, the fiber orientation within the reinforcement phase is crucial, making the design of composite parts more complicated than traditional CAD. Composite materials are ever present in everyday life. A common example is carbon fiber, which is commonly seen on aftermarket body parts in sports cars and frames of road bikes, typically seen in events like the Tour de France. Fiberglass is another example, commonly used for boat hulls and hot tub shells. Engineers frequently opt for composite parts due to their superior properties. Composites offer a favorable strength-to-weight ratio, resistance to corrosion and chemical degradation, are non-conductive, and possess exceptional durability. Going into now the benefits of composites, specifically when designing in CATIA. First, CATIA can handle large amounts of data. So composite parts, on average, contain more design data than the typical CAD model. Building off of a developed surface, each composite sheet or ply is comprised of a contour, material, and fiber orientation. To add to that, sequences, interactions between sequences, drop-off patterns, and areas to cut and splice plies are all defined in the model as well. And this is only a portion of what is defined. Handling heavy CAD models is CATIA's bread and butter. If you are familiar with CATIA's ability to handle large assemblies, you'll notice that it handles composite parts just as efficiently. Integration between analysis and design. Most CAD authoring softwares do not provide a link between the CAD, simulation, and manufacturing. Typically, the CAD is exported to a compatible format. Even more so, most composite definitions for CAD are built within the simulation software and not the CAD authoring software. The design process becomes complicated, and the composite definition is not linked to the CAD and instead must be manually recorded for design and manufacturing teams. 3DEXPERIENCE CATIA enables your CAD, manufacturing, and simulation data to all be linked within one platform database, eliminating the need to export and convert the data, resulting in more efficient and effective collaboration between disciplines and departments. Ability to predict manufacturing issues up front. CATIA offers a feature called Producibility for Hand Layup, which simulates the hand layup process and checks for issues that may occur, such as fiber deformation and sufficient roll width. And it is because of the features mentioned above that CATIA helps to reduce the design and manufacturing cycle times typically associated with composite parts. Composite Design Overview. Within CATIA Composites Design, there is a preliminary process of defining your plies and the order in which they stack up. This process can be accomplished using multiple approaches. Today, we will showcase the grid approach. In the grid approach, intersecting wireframes are placed on the base surface to define a grid. The intersections of this grid define cells. Laminates, which are defined as a preliminary step, are assigned to these cells. Doing so then defines contour and stack-up sequences of the plies. The grid approach is preferred for designing large and complex composite parts such as wings, fuselages, and wind blades, as well as designs that require structural elements to be considered such as stiffeners, stringers, and frames.
So the topic for our discussion today is going to revolve around a composite compound bow. Myself, I am an archery hunter, so I spend miles and miles and hours trudging through the forest every fall with a big, heavy compound bow. A trend in the archery industry and specifically the compound bow industry lately has been to move away from aluminum and steel bow risers and going more towards a composite structure. So I wanted to use that as sort of a springboard to develop this demonstration for you guys. So instead of hauling around a big heavy bow, maybe I get something that's a little bit lighter, but still has the really high strength to weight ratio that composites allows us. So that's where 3DEXPERIENCE comes in. I enlisted Tim's help to help me design a composite bow frame and give the layup properties and everything. I'm a simulation expert, so I can then take that design using 3DEXPERIENCE, map over all those composite properties, and then use that to validate the final design.
First, I will define my composite parameters, which consist of rosette, material type, and fiber directions. These parameters are utilized continuously throughout my design process. Optionally, I can also define here my laminates, main stacking sequence, and my ramp definitions. To define my rosette, I will select a predefined axis system which will dictate my fiber directions as they pertain to my part. We can see a visual representation of the rosette showing where the -45, 0, +45, and 90-degree orientations will be directed. Next, I will define the laminates which will be used. I can choose the color which represents the laminate, as well as how many layers of each fiber direction will be applied. I will design the composite definition of this part using the grid method. For this method, intersecting wireframes are developed on the base surface to define a grid. The intersections of this grid subsequently define cells. These cells are built with the intention of assigning laminates to them as well as defining the contours of my plies. I will only be using a single contour here, so the boundary of my part will suffice. The grid definition command allows me to define my cells where my composite laminates will be applied. Once again, I am only using a single contour for my first design, so I only have one cell. Double-clicking each cell available allows me to choose a laminate for that cell. The virtual stacking tool affords me the ability to combine cells and define the contour of each ply at every layer in the stack. fully defining the sequences in my design. A sequence is a stack of plies that results in a common thickness. The virtual stacking tool also enables me to add, remove, and modify plies and sequences. Therefore, this acts as a good tool to modify and update my plies. Plies are generated in the tree in 3D using Create Plies from Virtual Stacking Tool. These plies are represented as color-coded wireframes and surface representations. This tool provides 3 different algorithms to generate the plies: minimal crossing and weight saving only, and minimal crossing only. After I commit the plies from stacking, we can see that the plies are generated in 3D as well as the tree within a node called stacking. The plies created are grouped into their respective sequences. The sequences are placed into groups, where groups are essentially plies that share a common domain. Before I send this design along to simulation, I want to make sure it can be manufactured. Using the Producibility for Hand Layup tool, I can simulate how much deformation the plies will experience during the hand layup process and determine if that deformation is permissible. I have the option to include the effective thickness for each ply laid, or exclude it for a quicker solve time with lower accuracy. Choosing a seed point determines the first point of contact for the plies being laid. I can choose this point specifically, or I can utilize the tool to support a set of optimized points for me to choose from. My custom point is insufficient to build a simulation against, so I choose to let CATIA optimize my seed point for me. Once the optimization is run, CATIA outputs a set of seed points that I can then choose from. Previewing the producibility will generate the flat pattern, the roll width as it relates to the flat pattern, and the deformation of my plies. For the deformation, a warning deformation is reported as yellow lines, while deformations exceeding the limit are returned in red. Looking at my Results tab, we see that I can define here the warning and limit angles, as well as toggle the visibility for flat pattern, statistics, material limits, warp, and also animate the result. Looking at our producibility, we see some areas in red, indicating a deformation which exceeds our limit angles. Within the tool, we will create a dart to mitigate this failure. To create this dart, we will select 2 points that we created in 3D. In the scenario where the flat pattern exceeds the roll width of the material, we can choose options for splicing the numerous passes of the material roll, which accommodates the flat pattern. We can choose areas which will accommodate butt splices, no splices, as well as overlapping splices. Using the wireframe that I projected onto my surface, I define where the splice will be applied on my part. After I run the producibility, a node is created in the tree for each ply. Within this node, I have the option to flag the ply as either manufacturable or non-manufacturable to assist in issue tracking and resolution. At this stage, I am ready to send my data to the simulation team. But before I do that, I will show how we can build a solid from the plies. Typically, the solid is used for visualization purposes, such as checking for irregularities or voids, as well as providing a real enough representation to be used for renderings and presentations. The solid can also be used for light FEA analysis efforts, but in this webinar, I am simply showing you that it can be done. And finally, I will cut a dynamic section to show this result.
Thanks, Tim. What a good demo. I would like to take the next steps to talk to you guys about composite simulation now. We're going to shift gears a little bit. Mostly, I would like to talk to you about why composite simulation is so difficult, and then show you how 3DEXPERIENCE makes it easy. So as we all know by this point, composites are a combination of different materials. Usually you have a bunch of fiber fill with some sort of matrix that surrounds it, and these two materials together are better than either of them individually. So the reason this can be so difficult is these materials then have different strength properties in different directions. So if you load it along the axis of the fibers in terms of a unidirectional composite tape, then it's very strong. But out of that axis in the transverse, or even maybe in the like normal to plane direction, that structure can be a lot less rigid. So this makes for a very unique challenge when characterizing these materials from a simulation point of view. So 3DEXPERIENCE, powered by the Abacus solver, accomplishes this in a few different ways. So there's a few different approaches, as you can see on the screen here. First is micromechanics, material modeling. This is probably the least practical way of handling these sorts of composite interactions. But the way that this works is you actually model the fiber fill and the matrix directly, and you assign material properties to the individual bodies as they would be in the real world. So this is great for very small scale and maybe even sort of unit cell type applications. But once you get to a much larger structure or having fibers going in different directions, those types of things, and then you have to calculate all of the interactions between the fiber and the matrix around it, this becomes computationally demanding and not very practical to use on any sort of meaningful scale. So the second approach to composite simulation is to use the representative volume element method. So this essentially works in that you take your fiber and your matrix properties and you kind of take a representative sort of element out of those two. You figure out, okay, based on this unit cell element, how does this structure react? How is the stiffness different in these, different planar directions? And then you assign that representative stiffness as a homogeneous material to your metastructure, right, to the structure as a whole. So this is a very popular approach, and it's one that I'll kind of be working through in our demonstration today. And then for those among you who are a glutton for punishment, let's say, you can also define these material properties explicitly by actually inputting the orthotropic or anisotropic stiffness values directly into sort of a structural matrix environment. This is a very manual process, but if you happen to have these values from some sort of physical test or something like that, you can input them directly. So let's get into the simulation part of this demo. We're going to walk you through the steps to take what Tim already worked so hard on and incorporate that into the SIMULIA tools on 3DEXPERIENCE. So we're going to begin with meshing the components. We're going to map those composites that Tim worked so hard on onto our finite element model. We're going to build things up so that this thing behaves like a real bow and arrow. And then we're going to simulate it, right? We're going to build a scenario and look at some results. So let's get started. The first step to any good analysis in 3DEXPERIENCE simulation is creating the structural model. And this is done through Structural Model Creation app. So in here, you're going to see me create some nodes and elements. You're going to see me map those composite structures onto our digital model, and then we'll move on. So here you can see the bow as Tim has it designed. We're in the Structural Model Creation app. Next step is to begin some meshing. So I'm going to use a surface triangle mesh, and we're going to mesh each half of this structure individually. So you can see I've created a decent triangle mesh on the surface of this component for this half of our composite bow. I can change that element size down a little bit because it looks a little big. Want it to be a little bit smaller to accurately represent our loading. We're going to do something very similar to the other side. Select the body, enter sizes, create mesh, and based on the options that I have turned on, you can see I have a nice conformal mesh between the two halves of this structure, meaning that these nodes at the boundary between these two halves share a common node, right? So the elements share common nodes at this boundary so that the two halves won't come apart. From there, we can add in the shell properties for this composite bow definition. So I'll click on Composite Shell section, and I'll grab half of this model here. So I can define the layup explicitly, but we're going to pull it from the design directly from CATIA. And I'm going to do it based on the grid mapping that Tim already created. So I just simply go into the grid definition of that half of our bow here and enter it from there. So it really is that easy to map over the composite structures to the simulation stiffness definitions. All right. So I can specify my shell offset directions from here. And then we're going to do that same workflow just to the other side of this, this bow. So I'm going to grab the other half. We're going to pull our composite definition from the grid design that was already created. All right. And then again, we can go ahead and accept that. Next step here is we're going to build the rest of the bow. So I'm going to do this with what are called connector elements inside of 3DEXPERIENCE simulation. So I've gone through and created a bunch of couplings and reference points using CATIA to help me build sort of a skeleton structure of the rest of this bow. So in this case, you can see on my screen here, I have a beam element that I'm building up to represent the top arm of this bow. I'm assuming it's 10 millimeters in radius, and we're going to say, just for simplicity's sake, that it's built out of this 6061 T6 aluminum, right? You can see the material properties here. We can do both linear and nonlinear material behaviors in solid shells or beams. So we're going to choose the linear behavior here, and we click OK. So I'm just going to go through and create both of the arms of this bow using these connector elements and using the reference points that I've created with CATIA here to simulate this structure as a whole. So we're going through, it's going to be the same 10 millimeter radius on the bottom half of this. Again, we're going to go with a 6061 T6 and linear, click OK. And now I can go ahead and build the string as well. And this is done the same way, right? We're just grabbing the two ends of wherever this string happens to be. I'm going to speed up here a little bit. But in this case, I'm going to say it's a smaller diameter, and we're going to grab a nylon material. Most bowstrings are made out of a type of nylon, so we'll just go ahead and use that. I'm not super concerned about the arms and the string in this case. Really, I'm mostly concerned about the bow riser. So that's why I'm using these simplified connector definitions for this instead of modeling it all directly. But there on my screen, you can see the full assembly, well, virtual assembly made up. So in structural model creation, I used triangle elements with conformal meshes to mesh the two halves of this composite bow structure. So it shared nodes at the boundary so they won't come across or come apart, excuse me. And then I mapped the composite layup from CATIA using the from design dropdown in the shell definition. And then finally, I used connectors to model up the arms and the string of this bow, just to simplify the analysis a little bit. So the next step in creating a simulation is to do the scenario. So mechanical scenario is the app that's used to assign physics to the finite element model we just created. So in this, we're going to do a multi-step analysis, which is a technology enabled by the Abacus background of 3DEXPERIENCE simulation. So this allows me to do things like load the bow first in one step and then release using a totally different type of solver for a subsequent step, which is what we're going to do here. So we're going to load it with a static step and then unload it with a dynamic step, right? And the whole time when we're solving this, we're going to utilize the cloud compute that makes 3DEXPERIENCE so attractive from a simulation point of view. So let's take a look. So we'll launch the mechanical scenario creation app, and this will begin the setup for our physics assigned to our model. We'll select the finite element model I just created from the list. And the next step from here is going to be to begin our linear static step. So this is the first step in the study where we're going to load the model. We're going to pull the bowstring back. Okay. From here, we're going to assign our clamping load. So we're going to assume that my hand is a pretty rigid clamp on the bottom of this bow. This is just to hold it in place while we're pulling it back. It will probably over restrain that area, but that's okay. And then from here, we're going to assign a translation to the reference point that I have assigned to my arrow. So I'm going to say pull back this point on the bow and stretch it all the way back. We're going to say in this X direction here. And then my draw length is pretty long, about 305 millimeters in the negative X direction. So you can see the arrow update accordingly. All right. From here, we can move on to our second step, which is the release step. So this is going to be a dynamic response, right? We've added all of this tension, all this pre-stress to the structure. Now we're going to release it and see how the structure responds. So we can go into our feature manager here and turn off that applied translation, which is our draw load, right? We can say remove this load in the second step of the analysis. We're going to keep my hand on the bow so it doesn't fly off into space, obviously, but we're going to draw it back in the first step and release on the second step. And from here, all that's left to do is simulate it. So 3DEXPERIENCE simulation, many of the roles come with 8 cores of cloud compute for free, or you can buy credits to simulate with up to 192 cores. That's a bit overkill for this case, but that functionality does exist for larger models. So the scenario creation I always find to be the easiest part of the process. We did a multi-step analysis where really we only had 2 boundary conditions to assign. Holding on to the bow, pulling it back for our first step, and then second step is the release. So the scenario creation for this analysis was pretty straightforward. So let's get into the good stuff and look at some results. So simulation results are viewed via the Physics Results Explorer app. So this is like any simulation post-processor you might have seen before. We can create contour plots on the structure, we can do animations, we can look at XY plots to figure out, deflections and reaction forces and those types of things. But let's give you a taste of what post-processing looks like in 3DEXPERIENCE. So the analysis is completed. We'll close out this window. And here you can see my bow. We can go through the individual plot steps here. And you can see as I'm cycling through them, I'm slowly drawing this bow back. Now this is a worst case scenario, right? A real composite bow has cams and things on the end of this, but I'm not representing any of that here. I do see some areas of elevated stress in the corners towards the front of this bow riser, but let's take a look at an animation. So I drew it back and here you can see the dynamic release. And you can see how the bow actually has a little bit of sort of damping that's going into once the structure is released, how the string sort of bounces back and forth just a little bit before it comes back to rest. So we can look at other types of plots from here. This was a von Mises stress plot, but we can choose displacement. We can look at other steps. The post-processing is really straightforward with this tool. So we can cycle through each of these individual steps to try to find maybe where our maximum stress is in this second release step. We can use an XY field plot here to actually use one of our control nodes, in this case the arrow, and we can determine responses of this node. In this case, I want to know how this node moves in the X direction through the drawback and through the release. This will tell us sort of the amount that this is damping. So you can see that damp out of the arrow part of this string moving from there. Finally, we can look at composite specific failure criteria. So this is the Sci-Hill failure criteria that's very popular for composite structures. And you can see that we have very high elevated levels of stress located in these corners here. So this is the Sci-Wu criteria. It's very similar, but a little bit different way of measuring failure in composites. And then this is the maximum stress failure criteria. So each of these is a different way that is used to evaluate whether a composite will fail or not. We'll come back to those shortly. So from here, I want to go through and plot stress on different individual plies of my structure. So here you can see through the ply dropdown that I can go through and choose any of the 4 plies that Tim added to this composite bow. And I can view the stress on just that ply. So obviously this ply is only on this half, but we can see that I have a maximum principal stress on this of 23 megapascals in that inside corner, right? So that's a really neat trick with the 3DEXPERIENCE composite simulation and its integration with CATIA, is that I can view ply by ply individual failure criteria for any given part of this composite structure. So in the Physics Result Explorer app, we looked at our simulation outputs. We looked at a bunch of different contour plots. Specifically, we looked at psi-hill, psi-woo, maximum strain, and maximum stress plots. All of these read incredibly high levels of stress in those areas, indicating potential failure in the design. So based on my findings here, I need to then go back to Tim and say, hey, I need you to add maybe a few extra layers of material in these specific zones, and then he can just reopen that same model and add some of those layers in. So Tim, I'm going to turn it back to you.
I have been delivered the results from the simulation team and have identified the areas of failure. To resolve this, I will focus on the areas that failed and add material to reinforce them. Using my generative shape design app, I create planes in 3D which will be used to intersect my part. The wireframes that are generated will be integrated into my grid definition to build my reinforcement geometries. My reinforcements will consist of extra layers of material in the areas that failed, with their fibers oriented in a direction that provides more support to those areas. To capture this, I will modify my laminates with the Composite Parameters tool so the support patches are integrated into them. I will now redefine my grid definition by integrating the reinforcement wireframes I created earlier. I will do this by simply choosing all the wireframes. The boundaries of the cells to be created from these will be defined later. Here we can see that I have the ability to modify and define my draping direction. The draping direction determines the side of my mold that the composite material is applied to. Grid definition is where I will define my patches. Each intersection breaks out the boundary into different cells. These cells will determine where the laminates are applied. Within grid definition, I can dictate which laminates are applied to each cell. As we can see, the green laminates are being applied to the cells I want to place the patches on, as it contains the extra layer of composite material. I will reperform the virtual stacking to confirm my sequences and regenerate my plies. We see here that I can modify my sequences directly from the tool. I can toggle between sequence and ply-centric views. Using my ply view, I can see the order in which all my plies are laid, including my reinforcement plies. Next, I'll use the plies from virtual stacking tool to regenerate my plies in 3D as well as in my tree. We can see the new plies have been generated into my tree successfully within their respective sequences. With my plies regenerated, I will showcase some extra features available within the Composites design app, starting with core samples. The core sample tool allows me to pick multiple points to gather composites information from. These points have specific coordinates so I can reliably understand where the information is being reported from. I can gather information such as ply names, materials, fiber orientations, rosettes, sequences, and the applicable group. The thickness and number of plies can be gathered as well. I can cut sections through my plies while controlling the section scale to get a better view of my ply definition against specific planes. To do this, I simply choose my plies to cut, select a section plane, section type, and display type, and also choose a scale at which the section is going to be displayed. The Ply Exploder tool allows me to get a scaled view of my plies, but instead of focusing on a section, my entire ply definition is scaled. Running a section through my exploded plies, we can see each individual exploded surface. CATIA also offers the ability to create a range of drawings to represent my composite design. By pre-selecting my generation type to accommodate a composite-based part, I can easily create applicable drawing views just by selecting the plies group. Here, we see a view which shows the contours of my plies as they pertain to my mold, and next, I generate a view for my plies section. By choosing the correct generation type and selecting my stacking from 3D, I can create a stacking table which reports the plies group, sequence, plies, material, and orientation. Finally, I can choose to create a ply book. Within a ply book, each ply or sequence is assigned to their own drawing sheet. Each drawing sheet shows the individual ply or sequence in manufacturing position, making them ideal for developing manufacturing instruction and standard operating procedures. I will first create the template for how I want each cut piece to be represented in my ply book. For this, I have a top view showing where the ply is applied as it pertains to the mold, and also an isometric view of the ply by itself. I can choose whether each ply or cut piece has their own page, or if a page is dedicated to an entire sequence. Choosing the ply book command, and then my entire stacking will generate the ply book. And we see that each ply is generated on its own sheet while following the template that I built.
All right. So now that Tim has gone through and stiffened up this structure a little bit with some additional layers in certain areas, all I have to do is open up the model and rerun it with these updated parameters to view updated results. So really quickly, let's take a look at how that works. So again, here is the model with updated grid definitions. So you can see those listed here. But just to verify they've gone through to the structural model, I can walk into model plots and do a ply stack plot to verify that extra layers have been added to this model. So I can click somewhere outside of it and see that we have our original 4 layers of composite. Or I can click in the areas that needed a little bit of extra stiffening, like here, and again go into the ply stack plot and see that indeed extra layers have been added to this model to stiffen it. So comfortable with my results, all I have to do is go into the scenario app again, rerun this model, which it will run pretty quickly on the cloud, and view updated results. So here you can see that our Sci-Hill material failure criteria has gone down to 51. Our Sci-Wu criteria has gone down to just under 80. And finally, our maximum stress failure criteria has gone down to 57. So each of these were up orders of magnitude higher than this before stiffening up the structure. So simply by adding in a little bit of extra material, we've reduced the cross-sectional area, we've made this model more rigid in those areas. We can now say that, all right, this model is not likely to fail anymore. So let's compare results between the 2 layup designs. In the original layup design, which was all, just 4 layers of thickness throughout, our Sci-Hill failure criteria was 248. In the new layup design, we got that down to 51. Sci-Wu is a similar story. It was at 576, and we got it down to just under 80. And finally, our max stress failure criteria went down to 57, simply by adding in some extra composites in separate areas. And this is really only possible because of how 3DEXPERIENCE sort of marries together SIMULIA and CATIA functionality. CATIA is industry standard for composites, right? As you saw with Tim's demo, it does a great job of being able to layer up composites. Adding materials is easy. You can do it by grids and cells. And then SIMULIA, using the Abacus solver, is also industry standard in terms of finite element analysis. So 3DEXPERIENCE really brings these two tools together in a way like nothing else can, and it makes these types of iterative design scenarios much faster and much easier.
Moving on from here, we're about to wrap up our webinar for the day. I'd like to remind you, if you have any questions, please use the Q&A. Myself and the staff here were monitoring that. So to wrap up, I'd just like to tell everybody, thank you for coming. That concludes our presentation for today. Again, I'd like to thank you all for attending. If you have questions, comments, concerns, or want to see a little bit more about this functionality, please get in touch with our team, and we're more than happy to discuss this with you in more detail.